Hello everyone, my name is Tamanna Vohra and today I'll be presenting on digital DNA sequencing technology and application through flip-flops. This topic bridges the world of biology and electronics. Something we usually associate with computers is powering one of the most groundbreaking revolution in genomics. Let's start with the basics. DNA sequencing is the process of determining the exact order of nucleotides. Those are the A, T, C, and G letters you might have seen in genetics. It's like uncovering the instruction manual inside every organism. Whether it's finding a disease causing mutation or designing a personalized drug treatment, DNA sequencing is behind much of today's medical innovation. But what many people don't realize is that sequencing generates massive amount of data, which is where electronics step in. Digital DNA sequencing means we take biological signals like changes in current or voltage and convert them into binary data ones and zeros. This allows software and processor to handle, store and analyze the data at speeds unimaginable a decade ago. We have initially digitalized biology, making it searchable, shareable and programmable. It's the foundation of things like genome database and AI driven diagnosis. Think of digital electronics in sequencing like the operating system of a computer. It doesn't just execute one task, it manages power, timing, communication, and logic control all at once. Without a system like this, even the most advanced biology would remain unreadable chaos. Also, the scale of sequencing data is enormous. Millions of bases per second, and every single base must be correctly timed and stored. Flip-flop play a key role here, acting like traffic controllers for DNA information. They ensure that not a single bit arrives out of the turn. So in essence, digital electronics don't just support sequencing, they enable it happen at all. Let's zoom in on flip-flops now. At their core, flip-flops are bistable circuits. That means they can hold on two states, either 0 or 1. But that one bit of data is just the beginning. When you combine thousands of flip-flops, you create registers, counters, memory modules, essential building blocks of a digital brain. There are many types of flip-flops: SR, JK, T, and D. Each has slightly different behavior based on its input. In our case, the D flip-flop is especially useful because of its simplicity and reliability. It only transfers data when the system tells it to, on a clock signal, which makes it ideal for synchronous systems like DNA sequencing. So, why does that matter? Imagine a high-speed train. Each compartment represents a base of DNA. You don't want all compartments dumping their contents at once. You want controlled timing. D flip-flops ensure that each DNA base is captured exactly when needed. Not too early, not too late. Without them, data could overlap, misalign, or get corrupted. Sequencing needs to be exact. A single error can affect an entire genome analysis. That's why flip-flops, especially D-types, are a perfect fit for such precision-based technology. You can think of a D flip-flop like a memory block. The input is your data, the clock is the key, and the output is a secured vault. Let's take a closer look at a D flip-flop. When the clock pulses, it captures whatever value is at D input and stores it at Q output. Think of it like a trapdoor that opens only at precise moments, letting data through at the exact time it's supposed to. This timing control is critical, especially when you are dealing with thousands of bits per second from a sequencer. Flip-flops are Also helpful in sampling, DNA signals, tiny voltage or current changes are converted into binary values. Flip-flops are used to capture and hold those values at just the right moment based on the system clock. This ensures that what the machine reads is clean and accurate, not noisy or corrupted midstream. Now, sequencing doesn't happen in a perfect smooth flow. Data often needs to be held temporarily. This is where flip-flops act as a buffer. They store incoming DNA data temporarily while the processor catches up. This buffering prevents overflow and ensures that no part of DNA sequence is skipped or duplicated. Timing is everything in sequencing. Flip-flops help align signals, ensure each one arrives at the correct step in the process. Imagine trying to follow a conversation where people speak out of sync. It wouldn't make sense, right? Flip-flops bring order, signing all signals with the system clock for error-free processing. When you connect flip-flops in a chain, you get a shift register. It's like passing a note down a line of student. Each flip-flop holds a bit of the message and then passes it to the next. In sequencing, shift register hold the base data and shift it step by step into the next part of the system for processing. Since DNA bases are A, T, C and G, we need a way to represent this in binary. That's where encoding comes in. A is equal to 00, T is equal to 01, C is equal to 10 and G is equal to 11. Flip-flops store these codes, making it possible to run DNA data through digital logic systems and processors. It's like translating from a foreign language to binary. After a data is read, it must be held in place until it's processed. This is where latching comes in. A flip-flop acts like a gate that captures a value and keeps it stable. Even if new data comes in, the latched value won't change until a new clock pulse. This stability prevents errors and ensures that each base is correctly processed. As we know, no system is perfect, especially when data moves this fast. Flip-flops are part of error detection systems, storing parity bits. These parity bits help identify if any data was lost or flipped. In DNA sequencing, this kind of check can mean the difference between an accurate genome and one with fatal errors. State machines are logic circuits that remember what step the system is in. Flip-flops are the memory elements in these circuits. For example, in a sequencer, states might include read, store, analyze, and check error. Flip-flops update the machine's state with every clock pulse, keeping everything organized. In modern DNA sequencer, flip-flops are built right into the chip. They work invisibly in the background, storing data, managing signals, and executing logics. Without them, the machine would have no memory, no sequence control, and no precision. They are the unsung heroes of DNA tech. Speed and power efficiency are essential. Flip-flops operate fast within nanoseconds and consume minimal power. This makes them perfect for portable devices and field application. Imagine diagnosing a disease on the spot with a USB-sized device. That's only possible because of efficient digital design. The future holds even more promises. With advances like neuromorphic computing and new flip-flop architectures, sequencing could get faster, smaller, and more integrated. Imagine wearable sequencers or real-time genome monitoring during surgeries. Flip-flop will still be at the core, quietly doing their job. In summary, flip-flops help with storing, synchronizing, and managing digital DNA data. They are essential for making DNA sequencing fast, accurate, and practical in real world. By combining biology and digital electronics, we unlock powerful tools for healthcare research and beyond. These are the sources I used in preparing this presentation. They include technical papers, academic tutorials, and official documentation from digital electronics and bioinformatics communities. I hope this gave you a clearer view of how something as small as flip-flop can play such a big role in biology. Thank you for listening.